Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over another problem of how to calculate your delta, your free energy change, your standard free energy change from the standard cell potential. And so let's get into this. The problem that we're going to be dealing with in this video is this one right here. This is the reaction we're given. And we want to calculate the delta G of this reaction, the standard free energy of this reaction. And so what we need to do first is figure out what's being oxidized, what's being reduced. Here I have a table of the different half reactions that we're going to be looking at for this equation. I pulled these out of the actual table. So in the table of normally when you're looking up electrode potentials, you're going to be given a table, or you got to look up the table in your textbook of a list of different reduction half reactions. And so as you start high in the table, you get more positive values, and as you go down in the table, we get lower, more negative values. So it goes from positive to negative. And so higher in the table means that you're going to be much more strongly, you have a stronger tendency to uh, undergo reduction rather than oxidation. So the lower in the table, the more you're likely to go under oxidation versus anything that's above you on the table. So if you're higher on the table, if the substance is higher on the table, then that means it's going to be more likely undergo reduction compared to anything below it on the table. So this is what this mnemonic device means. Neo per. More negative is oxidation. More positive is reduction. So the more positive you are, the more likely you're going to undergo reduction. The more negative you are, or the less positive you are, the less likely you're going to undergo reduction. Okay, so let's get into this. So here, let's indicate the oxidation state. So sodium solid is in its standard state, so that's going to be a zero oxidation state. Water here for the oxygen is going to have a -2. Anytime oxygen is part of a compound, we give it an oxidation state of a -2, unless of course it's peroxide. And then that means that the hydrogen is going to be a +1, and we've got two hydrogens, so that balances out the charge to have a neutral charge because water is neutral. Hydrogen gas is in its standard state, so elements in their standard states again are zero. Here we have hydroxide with a negative charge. Again, oxygen is going to have a -2 oxidation state. And of course, again, hydrogen has a +1 oxidation state. And so the two added together, I only have one hydrogen, so the two added together gives us our negative charge. And then, of course, the oxidation state on your monoatomic ions is the charge itself. Okay, so we can see here that sodium is going from a zero oxidation state to a positive oxidation state. So it lost electrons. So that means it's undergoing oxidation. Remember, Leo-Gur, I should write that down over here. So another mnemonic device, Leo-Gur, or oil rig. Loss of electrons is oxidation. Gain of electrons is reduction. Oxidation is loss of electrons. Reduction is gaining electrons. So that's a good mnemonic device to help you remember what oxidation is and what reduction is. So sodium is losing electrons, going from zero oxidation state to positive, so lost negative electrons. So that is undergoing oxidation. And remember the mnemonic device, a red cat and an ox. So this is going to help you to remember what happens at each electrode, what happens at the cathode, what happens at the anode. So red cat, reduction happens at the cathode. And ox, oxidation happens at the anode, right? So sodium is undergoing oxidation, so we're going to have to write it here. So Na solid, and it's going to lose electrons, so it's going to become Na plus. Let me give myself some room here. Let me rewrite this, give myself some room. So Na solid goes to Na plus aqueous plus an electron. So we'll notice here that we have two NAs, so we're going to have 2 there plus the 2 Na pluses, and then that means we have 2 electrons being given off. So here's the half reaction for our equation, and that's oxidation, and that's happening at the anode. And then what's left over is what is being reduced. And we can see the reduction in the hydrogen. So hydrogen is going from a +1 oxidation state to 0. So it is becoming more negative. It's becoming less positive. So that means it's gaining electrons. So, and that's reduction. So let's write this down. So we have 2 H2O liquid, and that's becoming H2 gas, plus we have the 2 OH minus aqueous. So now we've broken this equation down in its 2 half reactions. So the sodium is being oxidized, the water is being reduced. Okay, so now here I have my table. This is my small table of my half reduction, half reactions, and I pulled out, these are the 2 that I'm interested in. And so you'll see that water is higher on the table than sodium. So you would expect water to be have a stronger tendency towards reduction compared to sodium. And you can see that from the electrode potentials. The standard electrode potential for the reduction of water is negative 0.83, and for the sodium it's negative 2.71. And if we remember our NeO-Per, more negative is oxidation, more positive is reduction. So compared to these two, the sodium is more negative. So more negative is oxidation. So this is more likely to undergo oxidation. Sodium will undergo oxidation rather than reduction. So water is going to undergo reduction, which is what we have here for our reaction, and sodium is undergoing oxidation. So this fits what we see in the table. So we can predict that this is probably going to be a spontaneous reaction. We're probably going to get a negative delta G from this, but let's go ahead and calculate it. So now we can go ahead and put this into our equation. So here I have E cell is equal to the electrode potential of at the cathode, and that's here. So remember, a red cat and an ox. So reduction here is happening at the cathode. So we have this one here, which is water, and we're going to plug in this value here. So this is going to be negative 0.83 volts minus, and then we'll add this one here, the electrode potential here for the anode. And then that's going to be a negative 2.71, so that's negative 2.71 volts. So now we add those together, and we end up getting, what do we get? Positive 1.88. So that's going to be a positive 1.88 volts. Let me double check that. Okay, that is correct. And so we got our standard electropotential of the cell. Now, again, you can plug it into this equation, or what you can do is add these reactions together to get the overall reaction, and then add those electropotentials together as well. So what you could do is then use the table here to get the electropotentials. So here we have water being reduced, and here it's already in the reduced form here. So we can just take this electrode potential and we'll put that there. So this is a negative 0.83 volts. And then for the sodium, we'll see here that sodium is being oxidized, is losing electrons, but here it's written in the gaining electrons form. So in order to get it into this form for our reaction, you'd have to flip it. But when you flip or reverse the reaction, you have to change the sign of the electropotential. So for this oxidation reaction going on here, the electropotential would be the positive of this. So it would be a positive 2.71 volts. So then when you add these two equations together, right, you add these together, you get, oops, I forgot electrons. Oh, I forgot the two electrons here. So here, this one is actually gaining plus 2 electrons. I forgot to put that in there. So this one's gaining electrons. And so the 2 electrons here would be canceled out with the 2 electrons here. And then when you add these together, you get this equation. We get the 2 sodium in a solid plus the 2 water, H2O liquid. And that's going to give us our H2 here, right? We have H2 gas, right? Plus the 2 OH minus aqueous plus our 2 sodium ions aqueous. And so when you add these together, you add these together. So then what you get here, just like you got here, minus a minus became positive, and then therefore you get a positive 1.88. You add these together, you're adding a negative, right? So you add, so your E cell, your standard E cell, then becomes these two added together, which is negative 0.83 volts. Plus the 2.71 volts, and then you end up getting the same answer, plus 1.88 volts. And so it works out the same way. So that's, again, this is where this equation comes from. When you flip this at the anode, oxidation, whichever one's being oxidized, you flip it and you take the negative of that value. That's what this negative is doing there. All right, so now we have our standard cell potential. We can now use the equation, this equation here. So our delta G is equal to the negative of N. In this case, the number of electrons. N is the number of electrons being transferred. We have 2 electrons, 2 electrons. So 2 moles of electrons is being transferred. That's what N is referring to here. So we have 2, and that's going to be moles. We have 2 moles of electrons. And then we're going to multiply that by Faraday's constant. So that's going to be 96,000. Let me double check here. 96,485. 485. And this is going to be coulombs per mole of electrons. Let me move this down so that this isn't in the way. So delta G, the standard free energy change, is equal to negative N, which is 2 moles of electrons, multiplied by 96,000, was it 45? 485. And that's coulombs per mole of electrons. And then that's going to be multiplied by your 1.88 volts. And remember, a volt is joules per coulomb. So we're just putting joules per coulomb. So we're going to put a positive 1.88 joules per coulomb. And so coulombs cancel out, moles of electrons cancels out, and then we're left with joules. So when we calculate this out, we get 3.6 times 10 to the 5 joules, and this is positive. Oh, nope, not positive, negative. I forgot the negative sign here. We have a negative here. So that is negative. And so you can see here that indeed, because our standard free energy change is negative, that means that this is indeed spontaneous, as we predicted from the fact that the water is higher on the table and therefore would spontaneously undergo reduction more readily than the sodium, which is found lower on the table. So putting these together, sodium would be the one that would undergo oxidation, which is exactly what we have in here. So the prediction was that it would be spontaneous, and indeed it is, because we got a delta G of negative. Okay, I hope this was helpful. I hope you enjoyed this video. If you learned anything from this video, then please like the video, share the video with your friends, hit that like button. Also, make sure you subscribe to my channel. Hit that notification bell so you can be notified by all the videos I put out. Make sure you click all. And finally, put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.